name is Baird, this is Nina, this is Jared, and that's Evan. And we are Team Gauntlet. And we made up a little acronym for that. The one we came up with is glove apparatus using new technological leads imminent today.
Our mission statement is we want to empower consumers with innovative, high-quality virtual reality experiences to advance the way that we interact with computers. We kept this at our core as we were developing this project.
So before we get into the meat of our presentation, let's give a little background on virtual reality. Virtual reality as a concept first emerged in the early 80s, about the same time as the movie Tron came out, that sort of thing. But 3D graphics at that time had not matured to the point where they could deliver on the promises that they made. And as a result, in the mid-1990s, interest in the subject collapsed, about the time that Virtual Boy Lawnmower Man came out, that sort of thing. But today, the subject is undergoing a resurgence in popularity, primarily being driven by a device called the Oculus Rift, which is the first promising device in the field of virtual reality in nearly 20 years. And from that, we were inspired to create the VR glove.
Okay, so the VR glove is a virtual reality glove, and what it does is it gives us a virtual representation of a physical hand in a virtual world. The whole point of it is to track the finger movement and absolute position of the palm. Our intention is to make it a fully interactive controller and eventually take it to market to become a consumer product. Products that were on the market and kind of are now are on opposite ends of the spectrum. You have the cheap products that are toy-like, they're not very good, they don't work very well. And then you have the industrialized, specialized products which cost tens of thousands of dollars that were developed by NASA and Lockheed Martin. And what we want to do is create something in the middle, a good product that works well, that we can afford, everyday people, for gaming and whatever you want to do with it. How our product solves problems. First thing, a natural method of interaction. In virtual reality, pretty much what you see is, it's just your view. You don't see any part of your body. So what we did is we created something that allows you to visually see your hand, give you some kind of feedback and more in-depth immersion. This also eliminates disorientation. Some people get dizzy, they get nauseous when it comes to using the Oculus Rift or virtual reality environment. And also what we decided to do was to minimize the cost by shifting a lot of the complexity into software. It takes away a lot of bulk and makes it more streamlined. Okay.
Okay, so when we were designing our device, there were a couple of key points that we wanted to hit. The first one was we wanted it to be low latency. The threshold for human detection between what you see and what you realize is about 40 milliseconds. And we wanted it to be below that threshold. We also wanted to have spatial tracking, which means how your hand moves in your environment rather than the articulation of the fingers. We also wanted to have one-to-one finger and hand motion. If you do this in reality, we wanted it to do that in the virtual world. If you bend your finger this much, same thing. And finally, we wanted it to be a consumer-level device, which means that we have to be able to manufacture it using cheap and commonly available components so that it would be inexpensive for the consumer as well as durable so that you could use it without fear of breaking it too easily. Next slide, please.
Okay, so here's kind of a list of the parts we use to make this a reality. We used, for our finger articulation and detection, we used a product called resistive bend sensors. And we used an Arduino microcontroller for our signal acquisition and processing. We use a product called a Razer Hydra, which is an off-the-shelf computer game controller that does absolute positioning pretty well, and so we kind of borrowed that functionality. We created 3D models for the computer in a piece of software called Blender, and we kind of tied it all together and with the Unity game engine, which is what it sounds like. It's a piece of software that renders a virtual environment, but it also has a useful functionality of being able, there's a lot of plugins for it, so we could tie all our hardware in through this one interface. And of course, we visually output, we display on the Oculus Rift headset.
So there's three major components in our hardware, basically. First, we have the virtual reality glove. That's the part that's actually connected to your hand. And that information, the information of those sensors that we have on the fingers are sent to the computer through a USB connection. Now, at the same time, we have the Razer Hydra, which is our positional tracking system. That as well is connected through USB to the computer. Then the Unity engine processes that information and outputs it through HDMI to our head-mounted display, which is the Oculus Rift. That in turn sends USB feedback to the computer about the user's head position. Now we use the Arduino Micro. It's a small microcontroller because we didn't need a lot of power. We're doing most of our processing on the computer side. So we chose something that's small, easy to use, and affordable. It's an 8-bit, 16 megahertz microcontroller. But the really interesting thing about this microcontroller is that it has native USB, which is much easier to use than just a standard microcontroller that uses FTDI to emulate a virtual port. It does have 20 digital I/O ports, but the thing we're really interested in is the analog inputs. That is how we're getting our signals from our sensors that are on each finger. And it's very easy to program. It uses the Arduino library. It's readily available, very easy to use, and all this stuff works just one-on-one with this microcontroller. Now on the computer side, we're using a plugin for Unity called Uniduino. Here's a picture of the configuration screen for it. It's very easy. You can change each pin, whether it's an input and output, whether you want analog, and it reports the values to you right here. It uses a piece of firmware called the Firmata firmware that makes this pretty easy to report. And it asynchronously reports ADC values at a sample rate determined in the firmware through basically on the Unity side, it's a virtual comm stereo port on that end, but it still uses the native interface in the microcontroller.
Okay. This is the component that provides our absolute positioning, the Razer Hydra. It's the off-the-shelf, commercially available piece of equipment that provides 6 degrees of freedom position tracking. And what that means is that it has 3 axes for both rotation as well as 3 axes for position tracking. And the way it accomplishes this is via induction. There's coils in both the hand receivers as well as in the base unit. It's easy to use, it's plug and play, and it's also easy to integrate into Unity since there's an integrated plugin available for use provided by 6S. Makes it nice. And for our head-mounted display, we're using the Oculus Rift. The particular model that we're using is the first generation dev kit. Provides 1 kilohertz sampling rate head tracking. It's used both glasses, has a bunch of interchangeable lenses for different base and head sizes, and it provides an output resolution of 1280 by 800 split across both eyes.
Okay. So one of the important things we had to do was finger tracking to really capture the movement of the fingers, and we did that with the device called a bin sensor, which it's manufactured by a company called Spectrasymbol. They're about 2.2 inches long, which is about like that, and they're resistive. And what that means is the resistance of the sensor varies with the angle at which it's bent. And fortunately for us, I did some testing on them because it didn't come with a very detailed data sheet. And the relationship between the bend and the resistance is pretty linear. And so we decided to treat it as such in our code. And we connected to the microcontroller with a really basic voltage divider circuit. And so the problem was, one problem we faced is, because we were using a voltage divider, when you have one element that varies in resistance and everything else to make our calculations easier in the computer. And that was actually a pretty simple matter. It was just rearranging a few equations, the equation for the voltage divider and the equation for the ADC value. But basically what we ended up doing was we kind of harnessed the fact that the sensor was linear, and so we just solved for the value of the sensor, and that's what we did all our processing with. And those are just the formulas. And another thing we had to figure out was, how does a finger move? So I did a little studying on it and some measurements. Basically, I broke the finger down into 3 joints, because that's how many are in a finger. For my purposes, I call them the bottom, middle, and top joints. And what I learned and what I observed, as it turns out, is that these 2 joints move independently. You can move them on their own. You can control them on their own. But the top joint, the finger, does not. It moves as a function of the middle joint. And I had to figure out what that function was. It turns out it's different for each finger. And this is an example. This is the actual data. And again, as you can tell, it's pretty close to linear. So again, we decided to treat it as such in our software. So basically, I deduced an equation, a linear equation for each finger. I just used my fingers, and so it's probably varies a little bit from person to person, but that's how we did that. All right. So when it came time to actually start building the hardware, it was pretty simple hardware, but we decided we wanted to make it compact and look nice, so we decided to make our own circuit for it. Actually, let me start with the sensors. Let me back up. So the sensors this surface right here is conductive, and we were sewing them inside cloth on a glove, and I was worried about noise and static. So what I decided to do was I got heat shrink tubing and insulated the sensor, which was nice because it allowed it to bend pretty freely still, but it shielded it from stray signals. And then, okay, when it came time to make the circuit board, we etched it. I designed it in a piece of software called Fritzing, which is open source and pretty easy to use. I made a layout, and then we etched it using the toner transfer process, which is basically a method of making a circuit board using a laser printer, photo paper, and a clothes iron. And then you etch it in some acid you can buy at an electronics store. And it worked out really well. That's a picture of the final board before we drilled it. And then we drilled it and soldered it.
Okay, so after the board was built and the sensors were put into the casings, the glove had to be constructed itself. We went with a glove that the material was thin, it was elastic, it could bend, it was durable, it was comfortable. And what we ended up doing is we stitched 2 pockets per finger, 1 for each sensor, with anti-static lens cleaning cloth. We just cut it, and then after we inserted the sensors, we stitched them down. And then here you have all the leads that lead to the circuit board. The circuit board is attached to like a foam mat that we cut and put Velcro on, so it's adjustable per person. And then on top of the leads itself, kind of to fasten them down and create a mount for the Hydra, we used another foam mat and then a foam baseboard. We had to put the Hydra controllers directly on. What we wanted to do initially was deconstruct the Hydra controllers and put that circuit for position tracking on the glove itself. What we realized is that the buttons on the top of it are hard to bypass. A lot of people have tried to do that and have not been successful, so we just put it on top of it.
So this is the flowchart of our software. This all happens in Unity because we basically report the values back using Arduino, and then we do our processing, software side, computer side, in order to make things simple, keep them together basically. So basically what happens is the values are captured from our analog to digital converter pins, and then our values are linearized. Those are the equations that Baird showed you earlier. From there, the values are basically normalized. It's basically a process in which it compares calibration values from two poses of the hand, a closed position and an open position, and then it's able to normalize between the values 0 and 1 to get that fully, where 0 is fully closed and 1 is fully open. And then from there we calibrate those, we interpolate those values from our 0 and 1 floating point values to an angle which we apply to the hand. Now if we need to calibrate those values because they're different for each hand, we have buttons that allow us to calibrate what those values are. And we will actually capture what those normalized values are, store them, and then when we normalize them here, we'll use those values again. This process is repeated about 60 times a second based on the frame rate of the simulation. So we used Unity. Unity is a little bit different than typical, C#, C++ programming in that you place objects into a scene, but you have a hierarchy view here. These are all your game objects that are in the scene, and you can organize them into structures, drag and drop them, move them around, and those relationships determine how these objects behave. But the last thing to understand about it is that you can attach a script to any of these objects. For instance, I could put an object into this, a script into this table that makes it move or explode or anything that I want it to. That can be programmed in either C# or Java. And an interesting thing to note about it is that it is actually compiled in a native code. It is the fastest, they claim it is the fastest implementation of Java available.
So in order to get those models into Unity, you have to make them simple first. Now, we have the option to using off-the-shelf stuff, which we download, but that wouldn't make for a very good learning experience. So what we did was use Blender. It's open source 3D modeling software. The models that it generates import natively into Unity. It's well documented. There's a large community, and it's easy to find resources for it. From no knowledge, I was able to make this hand over the course of a week, and it's using a tutorial that I was able to find on YouTube. It's very user-friendly, easy to use, and some details about the hand model. It contains just over 1,000 vertices, about 2,000 edges, and about 1,000 faces, and it's UV mapped using a 1024 by 1024 resolution texture. And over here, you can see the UV mapping as well as the mesh over here. Slide, please. So, any product is going to cost money to develop, and here's ours. We have a breakdown of all of the different components that the team members bought, and on our own private tracking, we also have who bought what, so we get reimbursed evenly at the end of the semester. So this top section is who spent, individual components. Down here we have the lab provided supplies. And finally, taking up the majority of the cost is labor, $8,000, which we calculated based on what four people making $6,000 a year would make over the course of 4 months, 40 hours a week. And lastly, to note, this $460 is the total value of all the components that we spent putting into the project. So, next slide, please. And here's what we hope it would cost for mass production if we were to bring this forward. The top component is the Atmega 32E4, which is the microcontroller using the Arduino Micro. Glove, pair, one for each hand. PCB/fabrication costs, bend sensors, got a 10 for each hand, so 20 total. Sewing costs, and the absolute positioning system. Now that's what we use the Hydra for in our prototype. Moving forward to production, we would probably want to use something that we create ourselves, cost $40. And for a total of $133, figure if we sell these at $200 per pair, we can make a nice profit.
Okay, so some of the problems originally we did parallel research between using bend sensors and accelerometers, and we decided to go with the bend sensors. The accelerometers, they were very complex mathematically. They needed algorithms to be done and compounded several times, which caused error, which would cause drift in the virtual reality. And so that became very complicated mathematically. And that kind of correction would have needed to use Kalman filters, which in themselves are very difficult to use. There's whole textbooks just on Kalman filters. And also the accelerometers we were going to use contain magnetometers, and the base of our Razor Hydra has inductive coils that creates a magnetic field. And what that would have done is it would have messed with the magnetometers on the accelerometers itself, and just given us off-the-wall data that wouldn't have done any good.
So we also wanted to use HID drivers for our glove. That's the same way that the Razor Hydra and the Oculus Rift communicate in Unity, but that was extremely complicated. I spent 4 days with 3 hours of sleep a day trying to figure that out, and you hire a consultant to do work like that, and they can have it done in a week. So instead we opted to use the Uniduino software. Also on Windows 8, we had trouble with Uniduino. We got the blue screen of death pretty frequently. We think it was because we know it was because the drivers in Windows, the USB drivers are, you basically have a buffer, and we were getting null pointers in that buffer because it ran out of information, and that would crash the computer basically. The blue screen of death in Windows 8 is little friendly faces. Pretty funny.
So, another road we kind of went down and ended up not going with was signal conditioning. And initially, when we hooked it up to the voltage divider, which is the easiest way to get a usable signal from the bend sensor, we wanted to use some op-amp signal conditioning to really cover the full range of the ADC, so we could get as much resolution as we could. So the problems were, I knew about op-amps theoretically. I'd learned about it in class, but I'd never really worked with them practically. And when it turns out there's a lot of parameters, and there's kind of a learning curve when you're actually using real devices. And so it took me a little while to figure that out. And initially I ordered parts that ended up not working because their specifications didn't really match what we needed. And eventually I did get the right device, and then when I got it, it didn't work. But I mean, that ultimately, after some discussion, we realized we had enough resolution on our ADC already with just the raw voltage coming out of the voltage divider that we could solve a lot of these problems in software, and we didn't necessarily need to cover the full range of the ADC. So we ultimately abandoned it. And it also, not having those extra chips really kind of matched our original philosophy, which was to keep the hardware as simple as possible and really put all the number crunching and complexity into our software.
Okay. So, future enhancements. Like I said, we use the Razor Hydra for absolute positioning. Future enhancements would be to actually create our own circuit to do that. We have a lot of our circuit board and our wires and everything is exposed on the glove. We'd like to create something that is where everything's concealed. You can't really mess with it. It can't be pulled accidentally. Also, a consolidated system. Currently, we have the Oculus Rift, the Razor Hydra, and the glove itself. And these are all separate components that are creating our project. And what would be really cool, and they each have their own USB, and what would be cool is having one system that works together through one USB. Our bend sensors, we use bend sensors that were available, that are pretty cheap. But we could probably do more research and get better ones that are more specific. And also moving off the wireless.
In conclusion, we created a glove, virtual reality glove, and it performed pretty well. We measured that our latency was about 3 frames, which is roughly 50 milliseconds, which is, it's well below the threshold of what a human, what an acceptable delay is. We concluded that signal conditioning circuits weren't necessary. We did all of our analog to digital conversions in software and just used those values directly. It integrated seamlessly with the Oculus Rift and the Razer Hydra Union, which was a major victory. And the bend sensors that we used were cost effective.
Okay. We just wanted to acknowledge a couple people. First is Dr. Yuan, who helped us a lot, gave us the idea of linearization. Her specialty is sensors, and that's a big part of our project.
We'd also like to thank our industry advisor, Vlad Bieber, who was a great help with both Unity as well as Blender.
We'd like to thank Dr. Mokes for being our professor for almost all 4 years of our undergraduate pursuits.
I'd like to thank Dr. McIntyre. He helped me with some op-amp problems when I was just pounding my head against the wall one day. And we'd also like to thank our TA, Cy, who donated a lot of extra time to us and allowed us to come into the lab for like 6 hours a day on weekends for like over a month. And that was a real big help. And everyone else.
We'd like to thank all you guys for being here. Congratulations on your graduation and good luck in your future pursuits. Thank you.
All right, thank you. Okay, we are really pressing on time, so if you have questions, ask them during demo time.
We'll have our demo out in the hallway.
Yes.
Yes.